afternoon, everybody. My name is Purvi. About a few years back, I was given an honor to run Kubernetes networking on GCP. And I was relatively new. I'm still relatively new. So it was out of selfish interest that I wanted to understand the evolution of Kubernetes networking and GCP networking and extract the principles that we could use to shape a better future. And a thought occurred to share this with larger community, hence this talk. The intention of this talk is to go over the evolution, as the title describes, of Kubernetes and GCP networking for Kubernetes, starting from beginning, the foundations, the abstractions that allowed us to take off, the abstractions that had to be adopted on both sides, to create a playbook for the right future. To kick this off, I'm going to introduce my co-speaker, Tim Hockin. As many of you know, he is one of the first engineers working on Kubernetes, and he has not only witnessed this co-evolution firsthand, but he helped shape it along with GCP networking team.
Thank you, Purvi. So I want to talk first just a little bit of background of why Kubernetes? Why is it exciting to people? And why did it catch hold? Why are we here in Spain with 8,000 of my best friends talking about this thing? And so from my perspective, I think there's a few really main points. I think Kubernetes is successful because we are ruthlessly focused on the application. And we didn't really want to conflate infrastructure with applications. And so you can see this in a bunch of different places in our API. And I think this gives us an opportunity to talk to application owners and application developers in a way that maybe other systems couldn't. At the same time, we had to be opinionated enough. We had to take certain opinions and positions on how we wanted things to work in order to derive the user experiences that we really wanted. Also, we accept from the beginning that platforms are going to vary. Right? The clouds that we're going to build on top of are going to have different capabilities, and Kubernetes accepts that from the beginning and plans for it. We've designed this system, obviously, to work with popular open source apps. And I think this is really the driving force that makes adoption of Kubernetes possible. We wanted to focus on patterns that people already know how to do, right? How to run MySQL. We didn't require you to change your applications, but we wanted to open new doors and change the way people think about how these sorts of applications would be run. You can't build a distributed cloud-native system without networking, right? Networking is really at the heart of Kubernetes, but it can be really hard. I'm not going to do a show of hands, but everybody struggles with networking at some point or another, and Kubernetes doesn't make it any easier if you don't know what you're doing at the beginning. So we really wanted to try to break through that. Networking varies between environments. If you get stuck, whether you're on premises or on a cloud, you have to learn about what's capable, what's possible in those environments. But application developers are not networking experts, and they shouldn't have to be. It's kind of ridiculous, the idea that if you want to build a full stack app, you need to understand layer 3 networking. So let's take a step back and maybe do a quick survey of where we came from, where we were at the beginning of Kubernetes and what was going on. So Kubernetes started with this system called Borg internally, and Borg's successor is Omega. We took the ideas from Borg and Omega. We really wanted to build on this idea of containerization. And as we started, we had to take a look around at what else was going on in the world when it came to networking, because Borg had some opinions, but maybe they weren't the best opinions. So let me start, and I'll tell you just a little bit about how Borg works with networking. Borg is all about shared machines, and they have a shared NIC. Everybody shares the resources on the machine. We didn't have namespaces. We didn't have virtual interfaces. We didn't have an overlay. We had the network. And so all the apps on a Borg machine have to cooperatively share the ports. If you want to open port 80 and you want to open port 80, you are both going to be in a world of hurt as life goes on. One of you would get it, one of you would not get it, and one of you would crash, and then the other person would get it. It was a nightmare. And so the end result was all ports were allocated by the Borg system. right? So part of the scheduling pass was you'd tell us how many ports you need, we would decide the ports for you, and then we would do variable expansion into your config language, so you could pass a -- port flag to your application, and then you had to use the port in the URL of your monitoring server so that you could find it, and the ports were going to change all the time because they were dynamic, and so if you took a URL and you sent it over Hangouts to your friend so they could go look at a bug report or something, well, the port might have changed by the time it got there. It was a mess. At the end of it, we needed our own naming system because DNS wasn't going to work for this anymore. And so you can sort of see how this design point propagates through the system, even to the extent that we wrote a kernel namespace to govern which ports you're allowed to open so that we could stop people from stepping on each other's toes. So 2013, what happened? Docker. Docker happened. We took a look at what Docker was doing. Docker took this idea of sharing a machine and they added namespaces. And man, namespaces simplified a ton of things, right? It gave you this really nice user experience. You've got a pretend machine with your own interface, but fundamentally it was still a machine-based model. Every machine is its own island. They get the same IPs. They're going to allocate IPs to the containers running on that machine. And if you want to talk between two different machines, you've got to come up with some sort of port mapping on the host, which will forward to your containers. And the packet gets translated at the edges, so you actually lose the source IP and you can't figure out the destination, or so the source port port and IP, sorry. And it's complicated in an entirely different way. And we didn't really like it. At the end of the day, how an app sees itself was not at all how other apps see it, right? I couldn't get my own IP address and tell you about it and expect you to be able to reach me. It was inconsistent. So from looking at these things, we sort of derived a couple of principles that we wanted to follow through as we were looking at Kubernetes and networking. Fundamentally, I have this idea that voluntary cooperative sharing of anything is a terrible idea. And it doesn't work at scale. And if you start with the assumption that everybody will be a good neighbor, you're going to have a bad time. Users should just not have to worry about collisions that they didn't cause. I want to listen on port 80. I don't care if somebody else wants to listen on port 80. I want to listen on port 80. It shouldn't be my problem if somebody else wants to. And so this is evident in the design of Kubernetes in a bunch of places, but probably nowhere more than networking. So we started with the Kubernetes model. Let's not share ports. Let's start with this assumption. We're not going to share ports. We're going to give every pod or every container an IP address, and not just an IP address, but a real IP address. The IP address that is reachable from other pods in the same cluster. So we don't have to fiddle with ports or mappings or -- port flags. We actually proposed this idea for Borg in about 2011, and given the scale of Borg and the equipment that we have running our network, we're told, you're crazy, get out of here, that's not feasible. So we put it on a shelf and we let it cook for a while. And when Kubernetes came out, we pulled this idea back off the shelf and said, what if we can do this? So we had to go take a look at what was available in the clouds, what the cloud providers could actually offer here. And frankly, it was pretty limited. Cloud networking circa 2013 was not very friendly, not very programmable. But we took another principle here. Is Kubernetes willing to be limited by what we can achieve today? No. We decided early on that we were not going to be limited by that. We were going to take some strategic bets on future technology. And so we bet on SDN and programmable networks. And we said, we're going to figure out the UX that we want our developers to have. So we took up this model. Everything is direct, flat network, no need for NAT, no need to manage port collisions. It works the way you would expect it to work. That was the idea. Now, can I actually make this work? Right? So we started to do some prototyping, some experimenting on Google Cloud. We did this proof of concept. We reached out to our networking team, a wonderful GCP networking team, and they said, who are you? Go away. We were nobody. Kubernetes was not a thing yet. And so we didn't have any leverage. We didn't have any ability to ask for changes to the networking stack. They said, this is what we have. Live with it. Okay. So we did. We took a step back, said, the networking APIs are very VM-centric, not surprising given that it was an infrastructure platform. What we were asking for is not part of the design space. So what are we going to do with that? Well, we found this little crack, and it's called the Routes API in Google Cloud. And it let us coax the network into carrying IP addresses to a VM that weren't specifically assigned to that VM. In order to do that, we had to disable things like IP spoofing protections, which is probably not a great idea. And we had to go out and configure, and we configured one static route per Kubernetes node. We had to do IP address management. This really did not scale well. The initial limit that we ran into was about 50 nodes. We could only get to about 50.
All right. So the fact that this worked basically was encouraging enough for us to press this issue forward. And the UX was really good. The IP per pod actually worked, and not only did it work, it looked simple, and all the things looked buttoned up. But the 50 routes were not going to scale that well. We knew it's not going to last long. So there was a lot of persuasion with GCP networking team, and the route limits were pushed to 100. And that is Kubernetes 1.0, which was shipped. Now, a question, does anybody know how many nodes Kubernetes 1.0 supported? And I gave the answer, 100. So, fact basically is that here is where the co-evolution of Kubernetes networking and GCP networking starts. And in the next few slides, in the next few minutes, we will go over how this evolution has gone through in terms of cluster networking, in terms of services and the load balancers, the L4 load balancers, and the L7 load balancers. Beginning with the cluster networking. The cluster networking worked based on route model, and it worked very well. And this drove the GCP networking team to scale the routes even more. We went from 50 to 5,000 in less than 2 years. And that drove major architectural changes within the GCP networking team, and it worked well. But there's a catch. And what's the catch here? There are a few issues that we just talked about, like IP spoofing disabled. We don't want that. But then there was something more than that, which is the IP for the pod ranges were not visible on the SDN, on Network Fabric. So the Google Cloud SDN had no way to reason what are the pod IPs. Now, if I want to do deeper integration with load balancer or telemetry, I have to infer from routes, which is not really the right way of going forward, and it's not going to work. Also, since these ranges were not visible on the SDN, you could imagine there could be future use of the same range, and that causes the collision. And last but not the least, even if the thing of this was a problem, the fact there could be overlapping ranges causes confusion, and it was hard to debug. All in all, we knew we can do better. So while we were scaling the routes, there was another angle which was going on in terms of how do we really get a better integration going in terms of different GCP networking products and Kubernetes. And the second, which you will see a pattern that will reoccur, how do we make it easy to reason, intuitive, and easy to debug? So the alias IPs actually were designed to address some of these issues, deeper integration, and easy to debug, and easy to maintain, and intuitive. Okay, so here is a GKE cluster. In this illustration, there are 2 nodes, and nodes get their range from VPC just like before. Even in the route mode, it got the same thing. And then, now the next thing, which is the pod ranges. The pod ranges and the service ranges now are allocated from VPC. So VPC knows that this is going to be a special use of this ranges by GKE. When the VM gets created, at that point, the per node pod range is also allocated in the form of alias IPs by the SDN. So now the network fabric actually understands the real IPs for the pod. And that is actually game changing, because up until now, the SDN had no way, the network fabric had no way to know the real pod IPs. Now it knows. Another simplicity of this is that per node IPAM went to SDN. So earlier, if the node was started, the Kubernetes had to stop its scheduling, get the per node range, give the node that range, then driver would be programmed, after which the scheduling would be unblocked. All of this is gone, and now they are exactly the same as any other instance groups in cloud networking. And the per pod the per pod IPAM is still within the node, just like in the Kubernetes using CNI. This solves all the other problems that we talked about. Future IP users is no problem, SDN knows about it, routes are not there to reason with, and things just work. This is where we basically integrated the container as a first-class endpoint in the network fabric of GCP.
So we've now got pod networking. And pod networking is now deeply integrated with the rest of the GCP network, which is fantastic. Pods are not the only networking construct that we need to deal with. Kubernetes services is a very fundamental part of the surface area and part of the model. I want to take a moment to look at the design of services. So services, specifically service type equals load balancer, was designed from the beginning to be centered on clouds, to make sure that we understood and adapted to clouds. Before I get too deep in that, I want to take a step back and highlight a key difference that sort of drove some of the design. There's two basic types of load balancers that you'll find in the various cloud products. There's virtual IP, VIP-like proxy, VIP-like load balancers, and proxy-like load balancers. And I'll talk a little bit about the differences between the two, and hopefully you'll see why it's important. So a VIP-like load balancer is always going to deliver packets to the end machine as if they came directly to the machine and not through the load balancer. The packet contains the destination IP of the VIP and the source IP of the original client. The load balancer is effectively transparent. And the assumption here is that the VM or the machine itself can respond directly to that client IP, and you don't need to go back through the load balancer. We call this direct server return or direct server response. And it's a very powerful system. Now, when you look at, this is how Google Cloud's network load balancer is implemented. When you look at this, the load balancer, again, it only understands VMs. Just like the network and the SDN only understood VMs, the load balancer only understands VMs. So we have to convert between a VM's VIP and a pod endpoint by running it through IP tables. So we have a set of IP tables rules. Anybody who's dealt with Kubernetes long enough has bumped their head against IP tables, I'm sure. And we use those IP tables to translate from a virtual IP into a particular service and then into a particular pod. The nice thing is it's implemented with basically the same set of rules that you use to implement the in-cluster service IPs. So it wasn't particularly onerous to implement this, but this is how VIP load balancers work. So now we talk to our friends at Other Cloud, and other clouds don't have a VIP-like load balancer, or didn't at the time anyway. They had a proxy-like load balancer. And a proxy-like load balancer is very different. It terminates that TCP connection, and it opens a new connection on the back. So what you see at the end is a packet that's from the load balancer to the VM, right? So I can now deliver the packet to the VM, but I have no idea which service you are actually trying to target. The VIP is gone. So we enter the Noda Port idea. Noda Port allocates a port from a reserved pool in Kubernetes and opens that port on all the machines in your cluster, all of them. And whenever you access that port on any machine, it's going to forward it into your service, and now you can tell based on that port number that you're destined for a specific service. And this is a simple primitive which we can then use. Then we can use to build these proxy-like load balancers. We can now target the VMs on a specific port, and now we have enough information to figure out which service you're talking to. Now, you can sort of see the difference between these two models, right? They require very different IP tables rules or very different on-node processing to set them up. VIP-like load balancers, that handles the same as in-cluster VIPs. Proxy-like load balancers are handled by node ports. I don't want users to experience that. That is not the UX that I wanted. If you have to write different YAML for different clouds, I have failed. So, how do we get past that? So the design of the Kubernetes service model is, we call it concentric. When you allocate a service, a plain old service, you're going to get a cluster IP. If you want a node port allocated to your service, you're going to get a cluster IP and a node port. And if you want a load balancer, you're going to get a cluster IP and a node port and a load balancer. What this lets us do is to translate your YAML into a consistent form. So now, if you're using a VIP, If you're using a VIPI load balancer, I can tell from the status load balancer ingress IP, I can inspect any packet and tell you're going for the particular service, in this case, front end. I can also tell if I'm receiving traffic on a local IP address and it's aimed at port 30669, which is allocated by the server, so you don't have to step on each other's toes again. I can also tell that you're going to the front-end service. So as an average user, I can write that really simple YAML, and I don't need to worry about the difference between the different cloud providers and the different environments. I'm going to get something that looks like this after all the defaulting has been applied, and it's going to work on the different providers.
All right. So we just went over the services and how services abstraction evolved to meet the load balancers. Now we'll go over the L7 load balancers. The Kubernetes introduced the Ingress resource to solve the load balance, to actually support L7 load balancers. And in those days, in the early days of Kubernetes, most of the load balancers targeted virtual machines or bare metal, but not the containers. And I would say most of the load balancers even today are proxy based. So if you were to then piggyback or learn from the previous few minutes where we talked about proxy targeting a cluster, use Noda Port. So Noda Port was a good starting point here. And let's start with that. Let's double click on Ingress. So in the Ingress resource, as we can see, it's pretty intuitive. It actually gives you L7 functionality, as in description of L7 functionality, TLS termination, URL path match, and then forward to service. When the Ingress API was introduced, I believe almost immediately there were many implementations that had shown up. And it's pretty much in the Kubernetes land, it's just an API, and implementations are different for each proxies. In Google's Kubernetes engine, we back it by GCLB, which is Google Cloud Load Balancer. And the way it works is that conceptually the traffic hits the ingress layer, which is load balancer. Once it hits the load balancer, then L7 functionality kicks in. After that, a service is identified, that is the Kubernetes service to send the traffic, which is type Noda Port, if you actually tie back into previous discussion. And then the service type Noda Port on the node would forward it to the right pod. Things look pretty simple and intuitive. However, when you start looking at the data path underneath, it's pretty complex. Most of the implementation on the node for all these node ports and all are either IP table based or the IPVS. We have it based on IP tables. We had it based on IP tables, and we still have it for this mode. In this case, you can see that the traffic, which is the blue dot, it goes from the client to load balancer, from load balancer to one of the nodes, and at the nodes, the IP table based random lookup happens, one of the pod gets picked up, which could be any of the node in the cluster, and then traffic hits the pod. So in order to make this happen, the way it is done is GKE, when the ingress resource is created, it actually creates an instance of GCLB, which is Google Cloud Load Balancer, and takes all the instances, all the nodes in the cluster, puts them into the instance group behind that load balancer. And this is how conceptually it gets done. As you can see here, that you could argue the balancing is good, because what if the pod distribution was asymmetrical? Some nodes had more pods, some nodes had less. So you kind of achieved a better load balancing by having this IP tables spraying the traffic. But then what happened is it came at a cost. The cost is performance. As you can see here, there's a double hop. You can assume latency, you can expect latency to go up. There is a network hop that comes in between. And it's, again, going back to the theme, easy to debug and easy to understand eventually for the customers. And then the last but not the least, some of the LB features are just incompatible with this mode. Let's double click on one of this feature which is not compatible. Example, cookie-based affinity. Load balancer GCLB supports cookie-based affinity. That's a very powerful feature for developers and users who would like to maximize the caching in the application, or they want to make sure that for the stateful application, client connection end up on the same backend. To make that happen, let's see how the packet flow goes through. The client sends a request to LB. LB does its load balancing, sends it to a node, and then IP tables on the node would randomly pick one pod. You started, response back, LB is going to insert the cookie in the response, which is going to specify the node. Next connection, when a client reaches back to the LB, that cookie is there, LB looks up the cookie and says, oh, this is for node A. And the traffic then, the request is forwarded to node A. The IP tables on node A is not cookie aware, so it does a random lookup again. And in the random lookup, what it comes is a pod on node A. So that feature is practically broken at this point, right? So while we were going through the alias IP-based container becoming the first-class endpoint on SDN, there was also a second thought, which was how do we really make this the first-class endpoint on the other products too, like load balancer? Why can't we load balance to the real IPs? NEGs were introduced exactly for this. NEGs is network endpoint groups. Basically, it's a grouping of the pods that can be then inserted into different products. For example, in this case, it's load balancer. Actually, this illustration is so boring that I don't even want to talk about it. The load balancer sends the traffic, and it goes directly to the pods. If I have to make it interesting, I can say, now see, there is no NAT, there is no confusion, there is no debugging hassles, and all the features like cookie-based affinity work. Which is one thing which I didn't mention earlier, is that cloud load balancer in the previous pattern was not able to really reason the load very well. Because it was sending to the nodes, and the nodes would do something else on the second hop, so it was not very accurate in load balancing. Now the load balancing is also accurate. So traffic shipping is right, and all the features work. So in the summary, in what we are seeing from the early Kubernetes to now, GCP networking evolved its support to make containers a first-class endpoint on the SDN, and also on many other products like telemetry and load balancers.
So that sounds amazing, right? This is a wonderful improvement, and for all of us sort of infrastructure nerds, it's a wonderful thing. For end users, it's a wonderful thing because now your features just work. But, of course, it doesn't actually just work. It turns out that programming external load balancers is a lot slower than programming IP tables. What I can do in sub 1 second in IP tables might take 10 or 15 seconds to program an external load balancer. We didn't really think of that when we were pushing pods and doing things in this super fast in-cluster mode. We need some way for the load balancer to check in with Kubernetes. So we're talking about the co-evolution here, right? That means both of us are going to evolve. So what do we need to do to make Kubernetes aware of these load balancers? So let's look at a real quick example of just sort of what could go wrong. Imagine now I've got my red deployment up, and I've got all my load balancer pointing to my red deployment pods, and everything's going great, and I decide I'm going to do a rolling update of my deployment, and I bring up a new pod, right? So we've got probes on our pods, as I'm sure all of you well-behaved Kubernetes users are using. The pod is alive, and the pod is in fact ready. It's ready to receive traffic, right? What do we know about the infrastructure at this point? What do we know about the load balancer? We know nothing. So if I'm a poorly behaved application controller, what I'm going to do is delete the old pod, and I'm going to start the process again, and I'm going to do the next pod, and then I'm going to do the next pod. All of those red load balancer links are going to go down before any of the green ones are going to come up. You've just experienced a total outage of your application by pushing a rolling update. This is exactly what Kubernetes is supposed to not do. So we have now a feature in Kubernetes that we call readiness gates, or pod ready ++. It allows arbitrary infrastructure to extend the definition of readiness so that you can feed back into these application controllers, the workload controllers like deployment, and tell them, hey, hold on a second, let me wait for the load balancer to check in. And I'm not going to get into the details of the API right now, but if anybody wants to talk about it, we'd be happy to talk about the details and the whys and wherefores. But now I can actually say, hey, this infrastructure is not ready, wait. And now all of my workload controllers, without actually being aware of the fact that there's a load balancer now, right? I've totally decoupled this. They know that they have to wait until these load balancers are up to date. And it's funny, we put this in front of our network SIG and we said, we've got this problem, we need to introduce this feature. And everybody in the SIG went, oh yeah, we know that problem. Why did nobody yell at me before? I don't know. Please, people, yell at me. So now we've got this, and we've got this synchronization point between the infrastructure and the pods, but it's all abstract, which I'm super happy about.
All right. So we went over now how GCP networking evolved to meet many of the abstractions, and then how Kubernetes abstraction has evolved to meet the cloud providers. Let's talk about one of the very key problem. How do we extend Kubernetes resources to express something that is very cloud provider centric? So most of the load balancers, they have features right now which are above and beyond what Kubernetes Ingress can specify. And as you go back to principle of portability, the main thing is if most implementation cannot support or most implementation should be able to support the most features. So with that, we were struggling in the beginning on how do we really specify the features of GCLB, which is the identity web proxy, CDN for caching, and security. And earlier we began with annotations. It very soon became bulky and hard to understand. Going back to the theme, how do we make it easy to understand and easy to manage? CRD came to the rescue. CRD is got introduced in 1.7, and that was a great way to extend an API. The users can now add a custom object and make it behave like a native resource. And that's exactly what we did. We introduced Backend Conflict as a CRD. The services would now point to Backend Conflict. In the Backend Conflict, the customers can go ahead and extend and express the features of GCLB, which were per services. And now they can be referenced by egress. We have a load balancer features now expressed in the CRD without affecting the portability of the ingress. So that is one of the key theme. How do we really extend without affecting the portability? How can customer take the same YAML, put it somewhere else, and things should just work? So we achieved it. So CRD has been great in that ways. All right. So now we went over abstractions on both sides, but there were a few things that we really found it difficult to overcome, or maybe we felt there may be something done better here. So let's go over some of the abstractions where we found either they were too flexible or not flexible enough. In terms of too flexible, the services has extremely powerful features of port remapping. You can have target port and the name port, and then the name port would then allow the ports to have their own ports, which would now give you lot of power to change the ports and stuff with each ref. But then that really puts it odd with some of the network fabrics. See, many of the load balancers, they would use DSR, which is direct server return pattern. This pattern is specifically made so that the high performance applications, they go through least latency. The response goes direct to the server while the request is going through the proxy. So there is no space for port remapping in that. With port remapping and the DSR, there is incompatibility. While this port remapping is a powerful feature inspired from Docker in the early days, if we go back and apply the filter of our portability principle that most implementations should be able to support the features, then this probably would not cut it in the main construct. Now, what are the things that were not flexible enough? We have seen use cases where customers want to forward traffic directly to the IP addresses, or maybe they have use cases where the ranges are wide and they want to express the range in their services, or the ranges are dynamic. VoIP applications are great here as an example. And service abstraction today doesn't have the flexibility to describe this. And then service abstraction is very intuitive when you are working with cluster IP and load balancer, and the moment you start going into, okay, how do I do the headless? Well, you have cluster IP type, and then you make cluster IP none. Things start becoming interesting when the same type starts behaving differently depending upon how different things are. there's a room for refactoring. And then we should have done the LB check-in a bit back. The LB primitives are not that refined right now, and the pod readiness could have been done long back.
So we're coming to the end of our time here. Looking at what we've talked about here, you can see sort of how Kubernetes has changed over time, how the design of Kubernetes was influenced by what the cloud providers could provide, but maybe not so limited by that, and how we at Google Cloud have tried to adapt to the things that Kubernetes offers to people to give better experiences with Kubernetes. I hope this gives you a little bit of insight into sort of where we were and where we are. But if you take away just one thing today, I would like it to be this. Networking is hard, it can be tricky, but it's getting better. And all the problems that you had last year, hopefully we'll take away half of them this year. And next year we'll get a half of what's left. We have a huge community of people in the open source community and at Google who are working their butts off to make networking easier to use, easier to understand, easier to reason about for Kubernetes users. We have a SIG network introduction and deep dive tomorrow afternoon. Anybody who wants to learn a little bit more about how networking Kubernetes works, please come to the intro. And if you want to get into the thorns and brambles of what's actually happening in the coming year within the network space, come for the deep dive section. We'll be happy to roll up our sleeves and get into it elbow deep. Thank you very much for your time today. We'll hang out here and do some questions. If people want to do questions, you can. Do we have time to do questions on mics? Let's do a few, and then we'll take it out in the hallway afterwards. Let me just pick up a couple from the front, and then we'll move back. So let's start with you.
What about IPv6?
What about IPv6? Come to the deep dive tomorrow. Other questions on the aisle? I'm sorry, I didn't hear. MTLS? TLS. Oh, TLS is a feature of the Ingress resource. So you can ask Ingress, whatever load balancer you're using for Ingress, to terminate TLS. One of the things we didn't talk about here is backside TLS or backside protocol. We actually have some annotation right now to do backside protocol. That's the sort of thing that should be moving into backend config or into a CRD if it's cloud specific. That one in particular, we're looking at maybe making a first-class feature of the API.
Any recommendations on how to migrate from old legacy clusters to VPC native clusters?
I'm sorry, what? So there's an unfortunate reality that the networking infrastructure from old GKE clusters and the VPC native networking infrastructure are very difficult to automatically migrate between. And we've looked at how to do the automatic migration. It's incredibly thorny and dangerous without understanding what's going on in your cluster. So far, the best recommendation we have for you is learn how to bring up a new cluster and move your workloads between them. It's actually a good skill. If you get too crystallized into one cluster, it becomes very difficult to recover from a disaster. So it's probably actually a really good thing for every organization to understand what happens if my cluster goes away. How do I bring up a new one, right? So I don't have a better answer than that.
Also, we can talk offline too on this topic further.
That's Purvi's team who's doing that work. Any other questions? Anyone down here? So service mesh, is Kubernetes going to deal with it? I do not want Kubernetes to become a service mesh. I want to understand what service meshes need so that they can use Kubernetes better. So like I talk with the Istio team fairly frequently and understanding what primitives they're building and why. It turns out they're working around things in Kubernetes. So we're going to see if we can find some core primitives between Istio and Linkerd and all the other options in service mesh so that we can make those things easier to build. There's obviously been some service mesh announcements already this week. We're talking all the time, but I want to draw the line at the single cluster for Kubernetes, and I don't want to build the mesh into Kubernetes itself. So is there a plan to release this stuff? So if you're using Kubernetes on GCP but not GKE, right? This already it works. You can use VPC native already. If you when you set up your VPC subnet, you can use IP aliases. You can create your instance group with the alias configuration. It'll automatically. There's nothing we're doing here that's private APIs or secret. This is all building on public GCP APIs. That's a core principle of the way we build Kubernetes at GCP. Is we don't have private APIs. Maybe the documentation could be better.
Could be. Okay, that's something we can look into.
Valid point.
Yeah, the open source Kubernetes on GCE would actually work.
You can. It's actually part of. I know it's not pleasant to say, but if you look at KubeUp, and you can dig through the shell script there, it'll actually turn on VPC native networks via a flag too. Other questions? Oh, there's one. Are there any CNI plugins for vanilla Kubernetes doing the same? I'm not sure that CNI has the scope to handle this. You need your load balancers to be aware of endpoints directly, which not all load balancer products are happy about. For example, we have to program the network endpoint group. Like during a rolling update, for every new pod, we go out and we change the network endpoint group and we resynchronize. Some load balancers are fine with this, and I know some folks like, I think it was eBay, has been doing this, the neg sort of idea, for literally years. Like they never even did the VM thing. Their load balancer does it automatically. And then there are others that are not as flexible or happy about being programmed dynamically. So it's more than just what CNI can do.
And the VPC native feature, which is the container on the SDN, is actually the function of SDN, which is a function of fabric. So a large part of cluster networking is taken into the platform within the network fabric and not in the CNI then. I
would love to see other platforms and other networking infrastructure sort of take on the same ideas, because I think it's a net good for users. Even though I love you all thinking that GCP is better than everybody else, this is a good thing for end users, like making the system better and more robust overall and integrating more deeply with the underlying systems. So we'll take the rest out in the hall if anybody wants to talk. Thank you.